All right, for the second example of 4.9, we are going to introduce something called finite differences, and we're going to see how that's used to determine the degree of a polynomial function if you know some of the data. So, first of all, a finite difference, what that means is finite difference just means in order to find the degree of a polynomial function, you just keep finding the differences between the y values of a function. So, for example, if we look at this one right here, we have x values for 1, 2, 3, 4, 5, 6, 7, and we have the corresponding y values. Um, to start taking the finite differences, what we want to do is take the difference of each of our y values. So the difference between 1 and 4 is 3. The difference between 4 and 10 is 6. The difference between 10 and 20 is 10. The difference between 20 and 35 is 15. The difference between 35 and 56, is 21. The difference between 56 and 84 is 28. This is called the first difference right here. This is called the first difference. Now, again, all we've done is we have to take consecutive y values. So if these were y values for like for x equals 1, 3, 5, 9, 18, if they weren't in order, these wouldn't be the differences. You have to take differences between consecutive points. So with finite differences, what we do is we keep repeating this process until we find a constant difference. Once we get to that constant difference, that will tell us what degree our polynomial function is. So again, this right here, just taking the difference of the y values, gives us our first difference. Now you'll notice 3, 6, 10, 15, 21, 28, these are not constant numbers. These values are all different. So let's go ahead and repeat the same process. So we're going to take the difference between our first difference values. Okay, so the difference between 3 and 6 is 3. Between 6 and 10 is 4. Between 10 and 15 is 5. 15 and 21 is 6. And 21 and 28 is 7. All I'm doing is I'm just taking the second number minus the first. So 6 minus 3 gives us 3. 10 minus 6 gives us 4. 15 minus 10 gives us 5. 21 minus 15 gives us 6. 28 minus 21 gives us 7. So these are called the second differences. Okay? Now, again, this is not a constant value yet. These numbers are all different. So we still don't know what degree our polynomial is. So now, finite means we just keep going one after another until we find a constant. So now we're going to do the same process over and over again, but on our second differences. So the difference between 3 and 4 is 1. The difference between 4 and 5 is 1. The difference between 5 and 6 is 1. And the difference between 6 and 7 is 1. These are all constant. They don't have to be 1, but once they are the same value, once they are all the same, then they are called constant. And once we get a constant, whatever level we're on, that is our polynomial. So this right here, this is our third difference. So what that means is that this is a third degree polynomial. So third degree. So that answers the first part of the question right here. Okay, we've taken some data points, and just by repeatedly finding the differences between the y values over and over again, once we get to the point where it's a constant difference, then we know what degree it is. Now, if these values weren't constant and we took the next set of differences, so the fourth differences, and those were constant, then this would be a fourth degree. If we did it to the fifth level and it was fifth degree, then it'd be a fifth degree polynomial. If we looked at x squared, okay, and we went and we made an xy table for them. So let's just say we took the values 1, 2, 3, 4, and 5. This is just an easy example just so you guys can see what we're talking about. The corresponding y values are 1, 4, 9, 16, and 25. Okay, so let's just show you what it would look like if we did this again. So if we went ahead and took the differences here, we would get the difference between 1 and 4 is 3, between 4 and 9 is 5, 9 and 16 is 7, and 16 and 25 is 9. Those are the first differences. They're still not constant. So if we do the second differences, you're going to see the difference between 3 and 5 is 2, 5 and 7 is 2, and 7 and 9 is 2. So these right here are our second differences, which means this would be a second degree. And obviously, if you look at our original function, x squared, we know that that is in fact a second degree. So just wanted to show you an example of this process for another function. So this will work for any polynomial. When you start taking the difference, once you get down to whatever level matches your degree, you're always going to get a constant difference. All right, so that answers the first part of the question. That's how we found that for this problem, we have a third degree polynomial. Now, it says use technology to find the polynomial function. So we're going to use regression for this. If you remember, we did linear regression and quadratic regression earlier in the chapter, or earlier in the year. That's where we have to use Desmos to work this out. So what we're going to do, we need to know our points right here. So in order to use regression to find the actual function, if we go to, let me see, we're going to go to Desmos right here. And what I've done is I've plugged in all of our points. These are the same points over here. Okay, 1, 2, 3, 4, 5, 6, 7, 1, 4, 10, 20, 35, 56, 84. You just get to that by, if you go up here and add a table, you'll get a table here. And then you just add those values in. So we already have that. Now, in order to figure out what our actual function is, we go ahead and do y1, then a tilde, and then we just type in our generic, since we know this is a third degree polynomial, we're just going to do ax1 to the third plus bx1 squared plus cx1 plus d. So that right there is our generic standard form for a trinomial. Now when we go down here, we get the parameters are 0.1667, 0.333, 0.5 for b. So we get our a, b, c, and d values. D right here is just 0. So now when we go back here, and you'll see this just goes through what I went through before. When we go through, these are the values we get for a, b, c. Now, a, this is just 1 over 6, b is 1/2, and c is 1/3. So when we take those values and we plug them in, this is our function that we get. Our original function is just 1 over 6 x cubed, because our a value is 1/6, plus 1/2 x squared, because our b value is 0.5, and plus 1/3 x, because our c value is 1/3. Again, you'll see that these are the same values that Desmos gave us right here for a, b, and c. Okay, so that's how you go ahead and use regression to do this. Now again, remember, with the finite differences, the thing I want to emphasize, we went down, this was a third difference example right here, but if these values weren't constants and we kept going and we found that our constants were on the fourth difference, then it would mean it was a fourth degree polynomial. A fifth difference means it was a fifth degree polynomial.